Welcome back, students. In this video, we are going to look at the exercise problems. I'll start with exercise problem 3.1. It says this: the storage battery of a car has an EMF of 12 volts. If the internal resistance of the battery is 0.4 ohm, what is the maximum current that can be drawn from the battery? This is 3.1. Okay. So you have a car battery of 12 volts. Okay. So this is 12 volts. And this has an internal resistance of 0.4 ohms. This is 0.4 ohms. Okay. So this is the battery. Okay. Okay. Now the question is, what is the maximum current that can be drawn from this battery? Okay. So when can you draw the maximum current? I mean, when you short circuit it. When you connect these two ends, then there is no resistance that is connected there. So then the maximum current will flow through it. Okay. Suppose that there is no resistance here too. If 0.4 ohm is not the resistance, then the stored resistance in the circuit would be 0 ohms. So then the current would be infinite. Okay. If this internal resistance were not present. But then there is this internal resistance which is part of the battery, but now I am going to short it. So I am not going to have an infinite amount of current. My current is going to be high, but it's going to be limited now. Okay. What is the current now? Well, the resistance is 4. Okay. I can do it straight away. This is 12 volts and then 0.4 ohms. 12 by 0.4 will give me the answer straight away. Okay. So that is one way of doing it, or the better way of doing it, just to get some practice, I am going to use the Kirchhoff's law. Okay. So let's do it this way. Okay. So let's assume that the current is flowing in this direction, and this is positive and this is negative. So let me start from this point and then I'll come back to that point again. Okay. I'll start at point A and come back here. Is there any resistance here? No. Then I come back. I enter into the battery through the negative terminal, so I have minus 12 volt. Then I enter through this resistance to the positive terminal, so plus I into 0.4, it's 0.4 I. Then I come back to A, so the potential drop is going to be 0, right? So which is simply 0.4 I equals 12. So I is equal to 12 by 0.4, and we want 20 by 4, so that is equal to 30 amps. Okay. It also tells you why your formula of the current is V divided by R is true. Okay, because of this. What have you got here? You got V here, you got R here. Why do you get even I is equal to V by R? It's because of Kirchhoff's law. Okay. So 30 amps is the answer for that problem. I'm done with it. And then we take up the second one. 3.2. A battery of EMF at 10 volts and internal resistance at 3 ohms is connected to a resistor. If the current in the circuit is 0.5 amperes, then what is the resistance of the resistor? Then what is the terminal voltage of the battery when the circuit is closed? Okay. So 3.2. What I got here? I got a battery of EMF of 10 volts. This is 10 volts. And internal resistance of 3 ohms. So that is this internal resistance of this battery. That is 3 ohms. Okay, so this is the battery now. Okay. And you are connecting it to a resistance. The value of the resistance is not given. So this is an unknown resistance. R. Okay. And what else is there? then the current in the circuit is 0.5 amperes. So when you do that, then this current is equal to 0.5 amperes. Then the question is, what is the value of the resistance? From your 10th standard, you might see that you got 3 ohms plus R. So that's they are connected in series, right? Connected in series. So 3 plus R would be the total resistance. 10 volts will be the resistance. So 10 divided by 3 plus R will be equal to 0.5, and from there you can find R. Okay, that is one way of doing it. Okay, let me do it that way too. So what's the resistance? Total resistance. Total resistance is equal to 3 plus R. Then the current is equal to 0.5, that is equal to 10, so divided by 3 plus R. So using this equation you can find R. It's a very simple problem, but let me do it through the Kirchhoff's law method. Okay, so that gives you some practice, right? So this is the current I have assumed. So this would be plus, this would be minus, and this would be, the current should go like this, right? So which means plus, and this is minus. Let me start from here and come back to the same position. Okay, and this is the direction in which I go through the loop. Okay, so now this is going to be IR, that's the voltage drop. I am entering the resistance to the positive one, so IR. Okay, and I come here, I enter the battery through negative terminal, so that is 10. And then I enter this resistance to the positive one, so that's going to be 3 into I. Okay, I is 0.5 and load again. So that is A. I'll come back to A, so which is equal to 0. So this is 0.5 R minus 10 plus 3 into 0.5. So 3 into 0.5 is equal to 0. So this is 3 into 0.5 is 1.5. 1.5 minus 10, that is minus 8.5. So I'll take it there. So my R is equal to minus plus 8.5 now. The minus 10 plus 1.5 minus 8.5 goes into plus 8.5 by 0.5. So that's simply 85 by 5, then it is 70. Same thing that you will get here too, right? So if I do it this way also, I'll get the same answer. Okay? Can you do it either way? But this will give you a practice with the Kirchhoff's law. Okay, which will come handy when you go when you try to solve bigger problems. So practice with this. Even though you can straight away solve it this way. Okay, so it's also another. It's very easy, right? When you can do it the other way too. So 10 by 3 plus R is actually 0.5. So 3 plus R will be equal to 10 by 0.5, which is 20. So R will be equal to 20 minus 3, 17. Okay. You don't even have to break any sweat to do this. It can be very easily done. But then use Kirchhoff's law so that you get practice. Okay. Third, 3.3. A. 3 resistors, 1 ohm, 2 ohm and 3 ohm are combined in series. What is the total resistance of the combination? This is something that you know from the 10th standard. So what is the combination? 1 ohm, 2 ohm and 3 ohm in series. So 1 plus 2 plus 3, that is 6 ohms. You're done. Then B. If the combination is connected to a battery of 12 volts and negligible resistance, obtain the potential drop across each resistor. Okay, we'll do it. 3.3. So what happens? So you have 1 ohm, 2 ohm and 3 ohm resistors. 1 ohm, 2 ohm and 3 ohm resistors, and this is connected to a battery of 12 volt with negligible internal resistance. So you don't have to worry about the internal resistance of the battery. Okay. So now simply you got 12 volts. Okay. They want you to find the potential drop across each other. Well, again, you can do it very easily. So 6 ohms is the total resistance, 12 volt is the voltage, then 12 by 6 will give you 2 amperes as the current, and then 2 amperes into 1, 2 volts, then 2 into 2, 4 volts, and 3 into 2, 6 volts. So you can do it that way also, which means 6 plus 4 plus 2, 12. You see, that 12 should be equal to this. You can do it that way also, as you have done in your 10th standard. But now I am going to use Kirchhoff's law, you said. So I know that this is going to be some resistance, some current I. So because I am assuming the current to flow in this direction, plus, minus, this is plus, minus, because current is entering this way, then coming back. Okay. So then I will start from this point and I will come back to the same point. This is my A point. Come back to that. I will use this. So I into 1, right? I into 1. So 1 into I. Then that is plus, because I am entering to the plus thing. Then plus 2 into I. Then again go through this. Plus 3 into I. Come back here. Then minus 12, because I am entering through the negative terminal. That must be equal to 0. So I get I plus 2I plus 3I is equal to 12. So 6I is equal to 12, and I must be equal to 2 amperes. Okay, it's very simple to do. Okay, then if I is equal to 2, then what is the potential drop? It will be 2 volts, and I into 2, this will be 4 volts, and this will be 3 into 2, 6 volts. You can see the 2 plus 4 plus 6, again 12, so 12 should be 0. Okay. So that's how we do this problem. Okay, that is 3.3 B part. Then 3.4. 3 resistors, 2 ohms, 4 ohms and 5 ohms are combined in parallel. Then what's the total resistance of the combination? That is the question. Okay. What is the total resistance of the combination? So 3.4 A. So 1, 2, then 3, right? So that is 2, 4, 5. So this is 2 ohms, this is 4 ohms, this is 5 ohms. So they are connected in parallel. So what do we know? We know that 1 by R is equal to 1 by R1 plus 1 by R2 plus 1 by R3. Okay? Spiral connection. So that is equal to 1 by 2 plus 1 by 4 plus 1 by 5. Okay? So 1 by R is equal, what can you take as the LCM? Can be 20. 20 should be fine. Or I can do it sideway, but we'll do it again. So 20. Then this will be 10 plus 5 plus 4, right? 4. So 90 by 20. So R equal to 20 by 90 ohms. So that's the effective resistance of this combination. Okay. Then what happens here is this. B part. If the combination is connected to a battery of EM of 20 volts and negligible internal resistance, then determine the current through each resistor and the total current drawn from the battery. That's easy again, right? So you have this structure, and now I'm going to connect it to a battery. Okay, and that battery is EM of 20 volts and negligible internal resistance, so I don't have to worry about the R, that small R part. I can completely ignore that. And this is what I've got. Okay, now this voltage will be applicable across all the 3 resistors. Okay, the voltage across 2 ohms is going to be 20, then 4 ohms is also equal to 20, and 5 ohms is also equal to 20. So then what would be the current here? So this would be 10 amps, because 20 by 2 is 10 amps, and this will be 20 by 5 amps, and this is 20 by 5, 4 amps. Okay, and that's it. And that gives you what's the total current. Okay, 10 amps here, 4 amps here, 5 amps here, and then 4 amps there. So totally this I is equal to I1 plus I2 plus I3. This is I1, this is I2, this is I3. I1 is 10, I2 is 5, and I3 is 4, so it's going to be 19 amps. Okay, so that will be the total thing. And that can be found using the effective resistance also, right? So 20 by 19 is the effective resistance, so 20 volts. So I can reduce this circuit to what? I can reduce circuit to a simple battery and then this resistance, right? So this is 20 volts and this is 20 by 19 resistance. So the current I is equal to V by R, so 20 by 19, so 19 will come there, so I is equal to 19. Okay, so either way you can do it. There are many ways of doing this. So one of the ways I'm saying the total current can be easily found by finding the effective resistance, or I can take this resistance. I know 20 volts is applied across this, so then I can find the current through each resistor, or I can use Kirchhoff's laws to do the same thing. Yeah, that's the same stuff. Okay, for this loop, what would I get? And for that loop, second loop, and third loop, I can use the same equation, and effectively I'll end up with the same result. Okay, so that is 3.4. So 3.5. At room temperature, which is 27 degrees Celsius, the resistance of a heating element is 100 ohms. Then what is the temperature of the element where resistance is found to be 117 ohms, given that the temperature coefficient of the material of the resistor is 1.7 into 10 to the power minus 4 per degree Coulomb. So that is a straightforward application because 3.5. But what do we know? For example, resistance at a different temperature is equal to R0 into 1 plus alpha into delta T. This is the expression we have come across in that lesson. So R0 is the basic, the original resistance or the reference resistance, and then this is a new resistance. Then alpha is given. So all that you need to do is to find delta T, right? So that's all. So okay, what is given? What is R and R0? Room temperature, this is 100. 1 plus, what is alpha? Alpha is 1.7 into 10 to the power minus 4. Delta T you don't know. Okay, so that's it. The next one, what is R? R is 170. Okay, so this is what you got here. Okay. I can take this in. I can do it different ways, but let me do it this way. So I got 100. We'll take it in 100 plus 1.7 10 power minus 4 into 10 power 2. So 1.7 into 10 power minus 2 into delta T, which is T minus T naught. It's a final minus initial. T minus T naught. Okay. So when I bring this here, 117 minus 100, 17 is equal to 1.7 into 10 power minus 2 into T minus T naught. That is my delta T. Minus 2, right? So what would I have here? So it's going to be 17 into 10 power minus 3. So when it comes here, it's 20,000 is equal to T minus, because 1.17 by 1.7 10 power minus 2 will give you 1000. Okay, so what is this then? That's a delta T. Delta T is 1000. But what is T naught? T naught is 27 degrees Celsius. So T minus 27 is 1000 degrees. So T is equal to 1027 degrees Celsius. So from room temperature, we go to 1027 degrees Celsius, then resistance changes from 100 ohms to 170 ohms. Okay? It is not, it's very easy to do the problem. That is 3.5. Okay, let's do problem 3.6. A negligibly small current is passed through a wire of length 15 meter and uniform cross section 6 into 10 power minus 7 meters squared, and its resistance is measured to be 5 ohms. Then what is the resistivity of the material at the temperature of the experiment? That's easy. So this is 3.6. So 3.6. So resistance, you know, that is equal to rho into L by A. The resistance value is given, that is 5 ohms. So this is 5, that is equal to rho, you don't know. L is 15 meters by A is 6 into 10 power minus 7 meters square. So 6 into 10 power minus 7 meters square. So this is 5 ohms, right? So this is 3, this is 3, and this will be 2. So this gives you rho to be equal to 2 into 10 power minus 7, 2 into 10 power minus 7 ohm meter. Ohm meter. So it's a very straightforward problem, nothing complicated about it. So that is done. 3.7. 3.7 is a silver wire has a resistance of 2.1 ohms at 27.5 degrees Celsius and a resistance of 2.7 ohm at 100 degrees Celsius. So determine the temperature coefficient of resistivity of silver. Well, there are two temperatures. One temperature is T naught, that is 27.5 degrees Celsius, and then T, that is 100 degrees Celsius. And the resistance at 27.5 degrees, I call this R naught, that is 2.1 ohm, so 2.1 ohm, and the resistance at 100 degrees Celsius is 2.7 ohms. Okay. Now they want you to find the temperature coefficient of resistivity of silver. That's easy, right? So what do you know? Like you know that R is equal to R naught into 1 plus alpha delta T. So delta T, this gives you delta T, 100 minus 27.5, that is going to be equal to 72.5 degree Celsius. That's the delta T part, right? So now I can plug all these things in. What is R? R is 2.7. Now R naught, the lower one, is 2.1, then 1 plus alpha into 72.5. Okay, so then you have this equation, then solve for alpha. It is so simple, right? So this is going to be equal to, so I say 2.1 plus, I'm multiplying the inside. So 2.1 into 72.5 to alpha. So what is alpha? Alpha is going to be equal to 2.7 minus 2.1. So it's going to be equal to 0.6. So divided by 2.1 into 72.5. Okay, that's the alpha value. So do the multiplication and division, then you must be able to get the alpha value. It's very simple, nothing complicated about it. Then 3.8, a heating element using nichrome connected to a 230 volt supply draws an initial current of 3.2 amperes which settles after a few seconds to a steady value of 2.8 amperes. Then what is the steady temperature of the heating element if the room temperature is 27 degrees Celsius? Then temperature coefficient of resistance of nichrome averaged over the temperature range involved is 1.7 into 10 power minus 4 degrees Celsius. So this is something that you already done. Okay, like the example problem. This is similar to that problem. So 3.8. What happens now? It first draws a current of 3.2 from 230 volts supply. So voltage given is 230. The initial current that it draws I is what? Is 3.2 amps. Then what is your starting resistance? 230 by 3.2. So my R naught is going to be equal to 230 by 3.2. I'll get some value for that. Okay, that is my R naught. Then what happens now? So as the current keeps flowing in the resistor, then heat is generated. Because of the heat generated, the resistance of the heating element changes. As the resistance changes, then the current reduces. How does it reduce? What does it reduce to? It reduces to 2.8 amperes. So now, for the same voltage, 230 volts, the current reduces to 2.8. So then what is your R1? So the same 230 by 2.8 is your R1. Okay. So now we got two resistances. Now what is expected? The temperature coefficient is also given, alpha is also given to be 1.7 into 10 power minus 4 per degree Celsius. Okay, so that is what is given. Alpha is also given. Then what is expected is what is the steady temperature of the heating element? Okay, if the room temperature is 27 degrees Celsius. So when you started this room temperature T0, which corresponds to this current, the initial current is 27 degrees Celsius. Then what is the steady state temperature? At the steady state, you are drawing only a current of 2.8, right? Which means the resistance has changed. So what is your steady state temperature? That is also very easy to do. So what is that? So your R1 is equal to R0 into 1 plus alpha into steady state temperature minus the room temperature T0. That's all. You have all the numbers there. So R1 is 230 by 2.8. R0 is 230 by 3.2, and then 1 plus your alpha is 1.7 10 power minus 4, and your T1 is what you need to find. Then your T0 is 27 degrees. So your one equation, we just need to find T. It's very easy to do. We just need to manipulate these numbers, and you should be able to do. So you will find T. Okay, it's not difficult to do. Okay. So the next problem. So the next problem is this, 3.9. So determine the currents in each branch of the network shown. Okay. You see 3.9 is this. 3.9, you have 10 ohms and then 5 ohms. It looks like Wheatstone bridge. And you have 5 ohms. Then you have 10 ohms. Then I have 5 ohms now. 5 ohms now. And what happens here? Again I have 10 ohms here. And then 10 volts here. Yeah. So they want you to find the current in each branch of the network. Okay. First of all, let us see if it is balanced. If it is balanced, then the center arm also will have no current, will bear no current, right? So if the circuit is balanced, the Wheatstone bridge is balanced. But is it balanced? Let's see, 10 by 5 is not the same as 5 by 10. This is 2, but that is half. Which means the circuit is not balanced. Which means this current, the current through the central branch, where you have connected the galvanometer, right? So that is not 0. So you have to do it the Kirchhoff's way. Okay? So you need to say that this is my I, okay? And this is my I1, this is my I2, and this is my, I don't know, maybe I3 I call. And what is this going to be? This would be I1 minus I3, right? So I1 minus I3. Okay? So now I3 is coming here, I2 is coming here. This is going to be I2 plus I3. I3 is coming here, I2 is coming here. So this must be I2 plus I3 using Kirchhoff's current law. Okay. At a junction, the amounts of current coming in must be equal to the amount of current leaving. Okay. So here I1 is coming here. So then that becomes I3. So this must be I1 minus I3. So I1 minus I3 plus I3 will give you I1. It's like that. So once I find this, once I have set the current like that, what should I do? I need to do plus minus. Then current is going like this. So this is plus, this is minus. Then current is going like this. So this is plus, this is minus. And then current is going like that. So that is plus, this is minus. Current is going like this. So this is plus, this is minus. And then you come here, current is going like this, right? So this will be plus, this will be minus. So you see, once you have fixed this, then it's a question of forming those equations, right? So I have this equation, 3 loops I can take. Okay. I've done that before. You can do it here, right? So let's see. So what happens here? I'll take the first one. So I'll start from this point A, come back to it. So this would be I1 into 10. So plus, right? I'm entering through plus 1. So 10 I1, and I come here, which is 5 I3, again plus, I'm entering through plus 5 I3, and then I come here, entering through negative, right? So that's going to be minus 5 I2. Minus 5 I2 equals 0. That is my first equation for that loop. Then for the second loop, then I start from here and then come back to the same position. So entering plus, right? So it's 5 into I1 minus I3. So maybe 5 into I1 minus I3. Okay? And come here, entering to negative 3, right? So it's going to be 10. So it's going to be then minus 10 into I2 plus I3. That's what I'm going to do. I2 plus I3. And again minus. So minus 5 I3. Minus 5 I3 is equal to 0 for this loop. Okay. Then reduce this. Get 5 I1. Is there any other I1? No. So it's going to be 5 I1. I2 minus 10 I2. That's all right. So minus 10 I2. What about I3? Minus 5, minus 10, then minus 5. So 5, 10, 5, minus 20 I3 equals 0. This is my equation 1, this is my equation 2, the second one. Okay, now third one. So this is the third equation, right? So let me start from here, maybe come back to the same thing. So I go here, here, okay. This is it, right? So this I2 into 5. So I2 to 5, then I go there. This is 10, again plus, right? Plus 10 I2 plus I3. Plus 10 I2 plus I3. And then I come here. So this is I. So what is I? I is simply I1 plus I2. I is I1 plus I2, right? So I into 10. So, no, sorry. I come here, then I enter through the battery, negative. So that is minus 10, and then I come to this resistance, which is 10 into I. And plus 10 into I. equals 0. We'll come back, right? So that would be, so it will be 5i2 plus 10i2 plus 10i3 minus 10 plus, instead of 10i, I'm going to have i1 plus i2. I is equal to i1 plus i2, right? So that's going to be 10i1 plus 10i2 equals 0. So how many i1s I have? 10. That's all. There's no other i2, right? So 10i1. Then how many i2s I have? I do 10i2. Then I get 10i2, so plus 20i2. Then how many i3s I have? No, I'm sorry. 10, i2 10, 10, and then 5, so 25i2. So 25i2. So i3 would be 10i3. That's all there is to it, right? No more. So plus 10i3 minus 10, that will go there 10. That is equation 3. Good. I got one equation. There are 3 equations. There are 3 unknowns, i1, i2, i3, and then there are 3 equations I got. I can even reduce these equations. Like I can divide the whole thing by 5. If I divide the whole thing by 5, what would happen to that one? So that's going to be 2i1 plus minus i2 plus i3. So divide the whole thing by 5. So 2i1 minus i2 and plus i3 equals 0. This is my equation 4. Okay. And I divide the whole thing, this also by 5. Then what would I get? So it will be i1 minus 2i2 and then minus 4i3 equals 0. That is my equation 5. And then I come here and divide the whole thing by 5 again. So I get 2i1 plus 5i2 plus 2 i3 equals 10. Well, I got 3 equations. I can either take these equations straight away and solve them. Okay, that is also a possibility, but I have just reduced this here. I can either take this set of 3 equations, or I can take this set of 3 equations and solve them. As we solved in the example problem. Then I should be able to find i1, i2, and i3, and that's about it. And that is going to give me the current in all the branches. So this will be i1, this will be i2, this will be i1, then this will be i3, i1, i2, i3, and this will be i1 minus i3, and this will be i2 plus i3, and this will be i1 plus i2. Okay, right. So that's it. You can do it this way. I hope this is clear to you. Okay, next is 3.10. This is a meter bridge problem. So in a meter bridge, figure 3.27, that is in the textbook, the balance point is found to be at 39.5 centimeter from the end A. When the resistor S is of 12.5 ohms, then determine the resistance of R. Why are the connections between resistors in a wheatstone or meter bridge made of thick copper strips? Okay. First of all, you're going to, okay, this is how it looks like, right? Okay, 3.10. Okay, so the meter bridge. It's like this. You have R here and then S here. R, S, and there is this wire, and here you have a Sharpie, galvanometer. This is a galvanometer, right? So this is the meter bridge basically. So first thing is, why are the connections between the resistors in wheatstone or meter bridge made of thick copper? So this will be a flat strip, if you remember. Okay, this will be a flat strip. Okay, again, and this will be flat again. A flat strip. this will be flat strip again. So this is a thick connection. So the thick connection is given here because you don't want this to have any resistance at all, or you want to have the connections to have negligible resistance. You want to have all the resistances to be concentrated here, R and S, and this must be of negligible resistance. So that is why the resistors, when you have a Wheatstone bridge or meter bridge, the connections between the resistors would be done using flat and thick copper strips. Okay, so that their resistances will be negligible. Okay, the connectors' resistances will be negligible. Okay, so that's the reason. Anyway, so this is A and this is B, and what is asked? So the balance point is 39.5. Okay, that is okay. And this is R, that is S. S is 12.5 ohms. This is equal to 12.5 ohms. So that is given. Well, determine the resistance of R. It is simple, right? So what do we know? We know that R by the balancing condition, R by 39.5, R by this resistance equivalent is equal to S by, what does this be? What will that be? That is 100 minus 39.5. That is 60.5. Okay? So same, R by, this one R by 39.5 is equal to 12.5 by, or S by this length. R by this length is equal to S by this length in the balancing condition, correct? Okay, so I'm going to make some approximations here. So this I'll take as R by 40, but you have to do it perfectly. I'm just giving you an idea. So this is 40, so that gives you S by 60. Okay? So 40 is 60. So what is S here? S is 12.5. So I can say this is 2 and this is 3 and take it there. So it will be 25 by 3. Okay. So that is roughly equal to 8.33 ohms. It's very easy to do. Okay. So you can do it this way. Or you can use the formula, right? So this is 100 minus 39.5, like it's going to be R is equal to LS divided by 100 minus L. That is the formula you can use, but this is much easier. R by this length is equal to S by that length. That's it. So you are done. Then B, determine the balance point of the bridge above if R and S are interchanged. Well, if R and S are interchanged, then what will happen? The balance point would still be the same, right? Like in the sense, it will not be the same, but then S by this length will be equal to R by that length, and it will just get shifted. Okay? So you will have, if you are interchanging this, if S comes here and then R goes there, then this length will come here and that length will go there. That's about it. Okay? So that's all. Nothing else will change. Okay? So the balance point will be shifted. Right? Instead of 39.5, it will be 60.5. That's it. From A, it will be 60.5. From B, it will be 39.5 only, if we change it. Not much change. Nothing else will change. Then C. So what happens if the galvanometer and the cell are interchanged at the balance point of the bridge? Will the galvanometer show any current? Well, no. Suppose you change this. Okay, this is a battery, right? I'm going to have a battery here. This is a battery, right? So this. Suppose I change the battery. Like here, in these 2 points. Will there be any change? No, there won't be any change at all. If you do the circuit again, it's going to be, right now it is like this. R, then S, then L1, and then L2. This is the circuit. Okay? And the battery is here, dynamic is here. Now if you connect the battery with this, and here this is going to be the galvanometer. If I change the position, since the battery will go there, the galvanometer will come there. And again, this would result in what? Okay, it's like this. Battery. Now you have this kind of, look at this now. So you have R, after R, you have two places. Okay, you have a galvanometer here, then you come, it's like this. This is R, this is S, this is L1, this is L2, and this is okay, like this. Even now it will be balanced, right? So R by S will be equal to L1 by L2. The same thing. Here, what we got here? R by L1 is equal to S by L2. That's what we have here right now. So now, if you bring this down, given this condition, R by S will be equal to L1 by L2. You see, when you have this condition, then also it is balanced. So under the balancing condition, you can have either this or this. And when you interchange these two, you are going to have R by S is equal to L1 by L2. So it will balance again. So even in that condition, there won't be any current through the galvanometer. So even if you interchange the battery with the galvanometer, there won't be any current through the galvanometer because it will still be in a balanced condition. Hope that's clear to you. Okay. So next one, 311. A storage battery of EM of 8 volts, an internal resistance 0.5 ohm is being charged by a 120 volt DC supply using a series resistor of 15.5 ohms. Okay. What is the terminal voltage of the battery during charging? Then what is the purpose of having a series resistor in the charging circuit? Let's try to see what's happening. 3.11. So you have a battery. Okay, another battery. So this is a bigger battery, this is a smaller battery. Okay, something like that. So this is 8 volts. It has an EMF of 8 volts and it also has an internal resistance R. And that is equal to 0.5 ohms. So this is this battery. Okay. So that is a battery. And this battery is going to be charged by 120 volt supply. This is 120 volts. The internal resistance is not given. So they are going to give you a series resistance of 15.5. Okay. Now they want you to find the terminal voltage. That is the voltage between the terminals of the battery. That's easy. Okay. How do you do it? I can use Kirchhoff's laws. Okay. Let me assume that the current is going this way because you are charging this battery with this, right? So this will be plus, this will be minus, and this will be plus, this will be minus. This current is going like this, right? So this is 8 volts. So it's like that. So now if I start here and then come back, doing the looping thing. So what I'm going to get now? So I'm starting here. So I into 15.5. So I 15.5 into I. That is positive because I'm entering through the positive terminal. And then I'm going to enter through this, right? Okay, good. So that is 0.5. So that is also plus. I'll enter here plus, right? So 0.5 into the same I. And then I'm entering through this battery at the positive terminal. So that is again plus 8 for a change. Then I come back and then I enter through this 120 through the negative terminal. So that is minus 120. equal to 0. Okay, so 15.5i plus 0.5i, that is 16i, that is 8 minus 120 minus 112, and that can go there, 112. So I can calculate I. I is equal to 112 by 16. Okay, so I can do this. So what can that be? 4 should work. This would be 2 4s are 8, and then 3 32, 8 4s are 32, and this would be 4, right? 4. Okay, 4 4s. So 28 base 4 is 7 amps. So 7 amp is the current going through it. I hope we have not made any mistake in calculating, but this is how you do it. Okay, 7 amp is the current which is going through this. Okay, now what is the terminal voltage? Well, 7 amp is the current that is going to go through this. Then what is the voltage drop across this? 7 into 0.5, it's going to be 3.5. Right? So that's 3.5 volt. So I'm talking about the potential drop between the terminals of the battery. These are the terminals, right? So what would be the potential across the battery? That would be, the potential difference between this and this. So what is happening there? This point, we start at this point, which is I call it as A, and go to B, and you see I enter like this, right? So VB, VAB. VAB is equal to, I enter like this, which is plus 3.5, and then I am again entering, right? So that is going to be plus 8. Okay, then I come here. Okay, so that is going to be 11.5 volts. So to charge an 8 volt battery, the terminal voltage must be 11.5. So that there is a drop of 3.5 across this resistor, and the remaining 8 volts would be used to charge this battery. So I can do it this way, or I can do it this way also. VAB, right? Okay, let me take this. What is this voltage? What is this voltage? It's going to be 15.5 into 7. Okay? So let's say, what is VAB? Another way of doing it. We go this way. If we go this way, this is minus. I mentioned through the minus thing, right? So minus 15.5 into 7. That is this voltage. And I am entering through the positive 120. So plus 120. And then I come back here. Okay? So this, if you do, this will also be equal to 11.5. Okay, volts. So to find the potential difference between A and B, I can go like this or I can go like this. In both ways, I will get the same value. Okay, so that is how we do this problem. And 3.12. In a potentiometer arrangement, a cell of EMF 1.25 volts gives a balance point at 35 centimeter length of the wire. If the cell is replaced by another cell and the balance point shifts to 63 centimeters, what is the EMF of the second cell? Okay, so what do we know? In potentiometer we know that E is equal to some phi into L, right? So this is what we come across. Okay, first is, what is that? First one is this. A cell of 1.25, so 1.25 gives you a length of 35 centimeters. So 5 into, say, 35 centimeters or 0.35 meter, whatever. So 35 centimeters into this 5 gives you 1.25. And what else happens? The next thing is another hole. Now you remove this cell and connect another cell. Then that gives you the balance point at 63 centimeters. Okay. then what is the voltage? That's the question. What is the EMF of this? EMF of this. Well, that is simply the value of phi into 63. Can I find value of phi here? Yes. So this gives me phi is equal to 1.25 by 35. So put it in here. So that gives you, this is equal to 1.25 into 63 by 35. So calculate this number, and that would be the EMF of the second cell. Okay, so it's a very simple problem. It's not very difficult to do. Then 3.13. Okay, the number density of free electrons in a copper conductor estimated in example 3.1 is 8.5 into 10 power 28 per meter cube. Now, how long does an electron take to drift from one end of a wire 3 meter long to its other end? The area of cross section of the wire is 2 into 10 power minus 6 meters square, and it is carrying a current of 3 amperes. Okay. So this is also a very simple problem. 3.13. First we have a conductor. Okay. The length of the conductor is given to be, 3 meters. And then the area of cross section is given to be this area. This area of cross section is given to be 2 into 10 power minus 6 meters square. So 2 into 10 power minus 6 meters square. And what else is there? And the amount of current that is flowing through this conductor, let's say this I, is equal to 3 amperes. And N, which is the number density of the electrons in the conductor, is given to be 8.5 into 10 power 28 per meter cube. So many charges, so many electrons per meter cube, the free electrons per meter cube. So all this is given. So now, so what do we know from this? We know that I is equal to Vena, right? I is equal to V-E-N-A, that is drift velocity. So current is given, which is 3, and then V-D I don't know, but drift velocity I don't know. E is 1.6 into 10 power minus 19, then N is 8.5 into 10 power 28, and then A is 2 into 10 power minus 6. So can I calculate VD from this? Okay, I'll calculate VD from this. So this will give me my VD. Okay, the sum number, I don't know, I call this a sum number N. VD is given. Then what's the length? 3 meters. So this is a drift velocity. So how long will it take? What's the drift velocity? Well, the electrons are the electrons will start moving from here with this velocity, and they need to cover 3 meters. Okay? Then how long will it take for an electron that enters at one end to come out of the other end? That's so simple, right? So the distance is given. So what is speed? Speed is equal to distance per time. So distance is given, time is what, the speed is given, t is what you need to find. So t is equal to d by v. So d is 3 meters divided by vd is something that you will calculate from here. So that vd you put, then that should give you the amount of time that the electron will take to go from this end to the other end. So it's a very simple problem. So we have covered all the 13 problems in this lesson. Some of the problems I have not fully worked out, but I have given you the idea as to how they have to be done, but that is more important. The rest is just multiplication, division, addition, subtraction. So that is something that anybody can handle. So that is not very important. The most important thing is to know how to approach a problem and solve that problem. And we have discussed that very clearly in this, I suppose. If you have any questions, if you have any doubts, if you are not able to understand any part of this discussion, please let me know, and I'll address that again for you. Okay. Other than that, I consider this lesson to be complete now. So the lesson number 3, current electricity, is done and dusted with the theory, the example problems, and also with the exercise problems. Okay. So lesson number 3 is over. So in the next video, we will take up lesson number 4.